Hello everyone, I am Shivam and I'm going to talk about our recent work here at KTH, where we replace attention with neural hidden Markov models or neural HMMs in text-to-speech. In this paper, we investigate the use of neural HMM in TTS. Our primary goals are to overcome the shortcomings of both HMMs and attention in TTS system, to use HMMs and deep neural networks together in a way that they complement each other to get the best of both worlds, and to provide a framework for faster iterations and training on small datasets when developing speech synthesizers. Why are we thinking about putting hidden Markov models in neural TTS? Let's do a quick overview of the old and new TTS paradigms. First, what are the appealing properties of classical statistical parametric speech synthesis or SPSS? It has a small footprint, it rapidly learns to align text and audio, it requires little data and is able to speak reasonably only from a few hundred training utterances. But SPSS also has a number of downsides. The state-wise nature of HMMs results in worse acoustic quality since each state has a constant mean output that doesn't changes over time. And we have to use hacks like dynamic features to smooth the generated feature trajectories. Even with this, we do not obtain lifelike prosody, since the output pitch is an average of all the possible intonation contours of the utterance, which sounds flat and boring. Each HMM state also has a constant transition probability. Mathematically, this means that the sound duration are assumed to follow a geometric distribution, which is a bad fit for natural speech. And each language requires extensive feature engineering to define useful linguistic feature extractors that are informative for good synthesis. Compared to SPSS, modern sequence-to-sequence neural TTS has several advantages. But for this talk, we will highlight the much higher synthesis quality, the more lively prosody, and the fact that this is achieved without the need for the same manual feature engineering as before. What is the reason for these improvements? Prior research has identified 4 key factors that are responsible for the difference between SPSS systems like Merlin and neural TTS systems like Tacotron 2 and DC-TTS. SPSS uses traditional vocoder parameters with an explicit F0 feature and feed these features into a signal processing based vocoder, while the new paradigm uses neural vocoders driven by MEL spectrogram. SPSS uses manually designed rule-based text analysis, while neural TTS uses an encoder network which can learn to extract relevant features directly from the text input phones itself. SPSS uses multiple HMM states per phone to increase the granularity of the modeling, whereas Tacotron and its derivatives use autoregression to enable predictions that are different for every time frame. SPSS uses left-to-right no-skip HMM to align the input and output sequences, while sequence-to-sequence neural network sequence-to-sequence systems use learned neural attention instead. Amongst these 4 differences, it turns out that the use of neural vocoders driven by MEL spectrogram significantly improves the perceived naturalness of the synthesis. The same for the learned text processing and use of autoregression when compared to earlier mechanism for frame-level position encoding. However, the use of neural attention was found to be problematic, and listeners actually preferred TTS using fixed alignments taken from a conventional left-to-right no-skip HMM instead. The key issue with neural attention is its non-monotonicity, which leads to a number of problems. We need many training updates to learn to speak. Here, even after 13,000 updates, the attention is not well formed. It can take a really long time to make attention-based TTS produce intelligible speech. Even after a lot of training, attention can still break down at synthesis time. Here are some examples of different utterances where the training model puts the attention all over the input sequence. This scrambles the order of phones in the sentence and leads to unintelligible gibberish. Finally, attention requires a substantial amount of data to work at all. When trained with only 500 utterances from LJ speech, monotonic alignment is never formed, and the model never produces intelligible speech. Because of these issues, improved attention mechanism that increases or enforces monotonicity are a hot research topic right now, and we review many recent methods in our paper. One of them from Nagoya Institute of Technology uses hidden semi-Markov models together with standard attention in a VAE and is included in the same session as ours. Our method, however, instead replaces neural attention completely. This is nice because then it is fully probabilistic and can maximize the exact sequence likelihood without approximation, and also does not need any external alignment tools for training. In a nutshell, our paper takes the 2 main paradigms for TTS, and fuses them together to get neural HMM TTS. In the rest of the presentation, we describe an example of how neural HMMs can replace attention using Tacotron 2 as our example architecture. But we emphasize that the same idea can be used for a large number of other neural architectures as well. Well, for instance, transformer TTS. By putting neural HMM inside sequence-sequence neural TTS, we obtain the best of both worlds. We can take advantage of learned text processing. We can use neural vocoders for better signal quality. Autoregression removes the limitations of HMMs. And because we are now using a left to right no skip HMM instead of attention, we can force the alignment to be monotonic and synthesize all the inputs in order. Also, instead of something like a stop token to decide when the utterance is over, we predict the state transition probability, which is the probability of moving on to the next state of HMM. In addition, we replace one of Tacotron 2's LSTM with a feed-forward neural network. This ensures that the process is Markovian and does not depend on previous hidden states. Finally, we also remove the postnet, which is not compatible with autoregressive likelihood-based models. One can easily add a postnet that's trained separately, which we consider to be a future work. The monotonicity of our HMMs give a significant advantage for both training and synthesis. It can make the model learn sharp, well-defined alignments with 500 updates, as seen in the first figure. And the output speech is intelligible after less than 2500 training updates, as the similarity between the synthetic and natural spectrogram shows. Integrating autoregression into HMMs addresses the main problem that HMM-based SPSS systems had. By looking at the previous observation when predicting the output parameters, the acoustics of the past frame can affect the next frame. This solves the issue that traditional HMM states always have the same statistics and significantly reduces over-smoothing across time. Regression also gives better duration distribution. Instead of a state having the same transition probability all the time, the transition probability can now change with every frame. This is very powerful. In fact, any discrete duration distribution can be described in this way. These rising patterns we see in the generated transition probabilities indicates that the model is aware of its progress through each speech sound, and the probability of switching to the next state gets high once we are near the end of the state. The transition probability also provides a natural way to decide when to stop synthesis. Tacotron 2 only stops talking when the probability of its stop token is greater than a half. That might never happen, leading to a synthesis that never stops. We instead use an approach from SPSS that aggregates transition probabilities over time, enabling us to generate the median, or rather any quantile of the duration distribution of each state. By adjusting our quantile threshold up or down, we can adjust the speaking rate even on a per state basis. This duration generation gives better result than those used in earlier works using transducers for TTS, which otherwise may have many mathematical similarities to neural HMMs. We've talked about the benefit of neural HMMs. Now let's take a quick look at how the model synthesizes the MEL spectrogram. We take the input text, run it through the regular text normalization, and phonetize it. We then pass the phonetized text to the encoder. The encoder then outputs a sequence of vectors where each vector defines a state in the neural HMM. For time step t, we select one of the state vectors based on HMM state the synthesizer is in at the current time step. That state is fed to the feed-forward layer in the decoder along with an autoregressive input based on the previous frame. To get this input, the previous frame is first passed through a prenet and then through an LSTM layer gives the autoregression long memory. The resulting output is then passed to the feed-forward network together with the state vector at time step t. The output net, which is the upper part of the decoder, defines the HMM's emission distribution. In this case, it returns the mean and standard deviation vectors of Gaussian distribution. It also computes the current transition probability tau. We use the mean to generate the tth frame of MEL spectrogram, and the transition probability decides whether to switch to the next state or stay in the current state, depending on the aggregated values of transition probabilities over time, thus completing the synthesis of the MEL spectrogram frame at time step t. We repeat this synthesis process for all time step capital T in order to synthesize the full utterance. We performed our experiments on LJ speech and considered 4 model configurations, 2 baselines, namely Tacotron 2 with postnet, which is called T2 plus P, and Tacotron 2 without postnet, which is called T2 minus P. This was compared to the same architecture, but using the proposed neural HMMs instead of attention. either using two states per phone, which we call NH2, or an ablation with only one state per phone called NH1. We compared the intelligibility, naturalness, and the size of the models. We evaluated intelligibility by synthesizing the validation set sentences at various points during training and running that audio through automatic speech recognition. This plot shows the resulting word error rate. Neural HMM TTS was able to generate intelligible speech after 1000 updates, while it took more than 15,000 updates for Tacotron 2 to do the same. Also, when training on small subset of the original data, Tacotron 2 never learned to speak at all, while Neural HMM was essentially unaffected. Now let's listen to some examples of synthesized speech at different updates during the training process. First, we start with Tacotron 2 at 2500 updates. And this is Neural HMM at 2500 updates.
The birch canoe slid on the smooth planks.
Even after 15,000 updates, Tacotron 2 sounds more like
the birch canoe slid on the smooth planks.
While the Neural HMM has even improved on the prosody.
The birch canoe slid on the smooth planks.
This is a significant improvement, especially when you want to iterate quickly in TTS research and development. For naturalness, we report the mean opinion score with 95% confidence interval on phonetically balanced Harvard sentences. The difference between NH2 and the most comparable Tacotron 2 configuration was less than 0.002 and was not statistically significant, despite NH2 being much smaller. Neural HMM benefited from using two states per phone, while Tacotron 2 improves with the use of postnet, which we plan to add in future work. We know that attention tends to break down on long utterances, but it also happens on short utterances as well. Let's listen to Tacotron 2 trying to synthesize potato.
Potato, potato.
Neural HMM TTS can speak this word flawlessly.
Potato.
The sentence test speech has a similar problem.
Test speech.
While for Neural HMM, it is just another utterance.
Test speech.
Finally, here are some examples of changing the speaking rate by adjusting which quantile of the duration distribution that we generate from. Something very slow.
The birch canoe slid on the smooth planks.
A little faster.
The birch canoe slid on the smooth planks.
A little faster.
The birch canoe slid on the smooth planks.
A little more faster.
The birch canoe slid on the smooth planks.
And the fastest.
The birch canoe slid on the smooth planks.
In conclusion, we have shown how to put together classic SPSS and modern neural TTS system to get the best of both worlds by replacing attention with a left to right HMM defined by a neural network. Compared to an attention-based neural TTS systems like Tacotron 2, this gives us a number of advantages. It is smaller and simpler. It learns to speak and align much quicker. It does not risk breaking down into gibberish. It's fully probabilistic. It allows easy control over the speaking rate, and it achieves the same naturalness. So next time when experimenting, if you need something which is faster to train while developing, or you don't have enough data to train an attention-based model, use neural HMMs. Please scan the QR code or visit the link directly to listen to more audio examples. You can find our code and a pre-trained model there. Thank you for your attention.